Buenos días, gracias por estar aquí a esta interesante charla. Hoy tenemos la suerte de tener a Mauricio Ercoli, que nos une una relación de ya unos cuantos años y de hecho ya hemos colaborado, tenemos estudiantes que han venido a este instituto y por tanto es un placer presentarte y que hagas esta charla para nosotros. Ha hecho mucho más fácil mi trabajo porque ya veis, ha puesto una diapositiva con todo su perfil. Mauro hizo la tesis él es geólogo, hizo la tesis en Perugia y él inicialmente trabajó sobre todo con temas de GPR, de georradar, y poco a poco con el tiempo se ha ido moviendo hacia temas más de sismología, de sísmica y de sísmica activa. Y bueno, pues eso, ¿no? Tenéis un poco ahí los tópicos o a qué se dedica él, todo lo que es la parte de procesado de datos sísmicos, interpretación y utilizar todos estos datos para su aplicación. Y sobre todo, una de las partes importantes que hoy hablará es la parte importante de los atributos sísmicos, que creo que es una parte muy exacto y que es muy interesante y que ya veréis que podéis ver que además aprovecha el tiempo para hacer muchas colaboraciones y viajar por el mundo y estará durante esta semana aquí entre nosotros, o sea, si alguien quiere pues hablar con él o estará en la planta de arriba y hasta el viernes, ¿no? Till Friday. Okay. So, no, you have the mic. So, thank you.
Thank you for introducing. Okay, it's better now? It works? Yes? Okay. Okay. So, today I'm going to introduce to you some examples of application of techniques, post-stack techniques, data preconditioning and seismic attribute analysis on legacy seismic reflection data. In particular, we work with my group in the Università of Perugia, structural geology and geophysical group. We work several years. We work on the some seismic sequences we had in central Italy, and with seismotectonic applications. So I'm trying with these techniques to unveil, to extract some data that are not visible in the original reflection seismic line. So we had this idea to trying to exploit this possibility and to test some applications. I will make a quick overview on the legacy data and their possible use for seismotectonic application. And I will quickly introduce, I promise, the seismic preconditioning techniques and the attribute analysis. And then I will show you a couple of examples from the central Italian region in Central Apennines on commercial profiles derived by industry. And another example on a deep seismic reflection line, the crop 4, crossing the southern Apennine fault thrust and belt that was struck in the 1980 by a strong earthquake, and then some conclusions. So let's start with seismotectonics. As you already possibly know, seismotectonics investigate the relationship between the seismic activity. So earthquakes the epicentral depth and the tectonic structures that we can map at the surface. The structural geologist map at the surface. Like this is a seismic geological section, structural section extracted in central Italy from the area that I will show you. And as you know, the geologists map the faults, the thrust, the normal faults. But then there is once we have a strong earthquake like this earthquake that was in central Italy in the 2016. Magnitude 6.5, we have, of course, a gap that we need to fill from the surface to the epicentral depth. And thus, which is the best way to, of course, to fill this gap, to try to reconstruct the geometry and the kinematic of the faults, is geophysics, but in particular reflection seismic. That is the method. When I was preparing this talk, I found these nice images in a blog, agilescientific.com, in paper Michenko. That's 4 years ago, was the 100 years from the first reflection seismic experiment performed in Oklahoma by this group of physicists and geologists. A lot of time passed, and this was for exploration, a lot of evolution, 3D data, and so on. But it was nice that they had this intuition, they developed the instrumentation, and they performed the 1921, the first experiment, and they had this intuition that this method worked very well to understand, to image, to determine the geological holding in the subsurface, and in particular, they say this invention has a special application in the location of anticlines, faults, and the other structures, of course, for exploration. Then they drilled the first well a few years later. We are in the academy. We are interested not in the exploration, but in this case in seismotectonic. And so here in Italy, the reflection seismic exploration started later in the 1930 or so in the Pianura Plain and the Pianura Padana Plain. But then the big, the best period was in the 80s, 90s. Where the companies were running a lot of seismic campaigns, and the data that were collected at that time are now available in this database, Italian database that is VIDEPI, Visibility of Petroleum Exploration Data in Italy. As the permits expired, they published the data. And we can find there is a WebGIS online where you can download the data. I will show you which kind of data they are. Then there was another interesting project, again in this period, the 80-90, that was the CROP project. It was for research, multidisciplinary research, to study the Italian lithosphere, so different type of reflection seismic line, deeper, to investigate the lithosphere. And this was cooperation between private and public academic and research center in Italy, and they collected, as you see in this image on the right, you see several long transects offshore and onshore, and we reprocessed, and for the second application, the second example I will show you, the crop 04 in southern Italy. It's similar to, this project is similar to the I think the Ibercis that you have in Spain also. Legacy data, why they are important? They are important because they are possibly the unique data we have in seismic areas. Okay, maybe they are not so good in quality. This is an example of a seismic line, the reservoir scale, the industry, the derivation is from the industry. But they are possibly not ideal for our faults that we want to study. They have an orientation that is not ideal. They were collected with old equipment, and they were processed with relatively old techniques, if we think that to what we have today, no? But these are the unique we have, and sometimes we, instead of collecting or before collecting possibly new data that require a lot of efforts in terms of logistics and cost, it's better to to use them and to try. My intuition at the beginning was I look at this profile and that were generally, you see, sometimes they are stuck, post-stuck, or time-migrated lines, so with relatively low quality, and therefore, for every line, I mean, there are many interpretations possible, no? Because in the areas where the data are particularly noisy, you can draw up faults, of course, with all the geological knowledge, but it's more subjective. So I know about the industry application that there are several tools that allow us to improve the quality of this data, and I say, okay, let's try to test, and I tried. And this is another example of the crop. This is the crop in the crossing the Umbria-Marche region. Is as you see, it's deeper because we have here, it's not very visible, but we have 16 seconds instead of the 6-8 of the commercial lines. The target was different, as we said, and the reflectivity is very, very scarce. In particular, something better at the surface, but depth we have pure signal and noise. And we have this kind of data in PDF format. The crop is possible to have the digital data, but for the VDEPI lines, this is a database that we have in UniPG that is a great database done by our former collaborator, and we reported the lines that are available from VDEPI. These are the commercial lines. And then we have other lines. These are the crop, the violet, the crop. You see the longer transects. And instead, the yellow are the lines that we obtained under confidential agreements by the companies like Eni in Italy or others for studying specific areas, in particular after the earthquake sequences. So I say, okay, just an introduction on the seismic attributes for the ones that maybe are not, aware of this possibility. Seismic attributes is a tool that has been developed in the industry starting from the 1960s and 70s. In particular, during the seismic crisis, they have huge development and can be defined as any kind of measure in seismic data that help us following Marfur. Then is down the icon, but is the Marfur in 2006 to say that this is any measure in seismic data that can better help us to visualize or quantify feature of interest for our interpretation. And so, for example, faults or stratigraphic features. They can be of different types. The first instantaneous attributes where you find information in this nice paper by Tanner in 1979, complex seismic trace analysis. Then, of course, there was a huge evolution till nowadays, the machine learning techniques also using attributes, and they can be computed on the sample, on the trace, on the line, or on the 3D volumes, and or across horizons or time slice in 3D data. So they can be based on the amplitude, on the phase, on the frequency, and on the correlation, on the similarity among the traces in a 3D volume, like in this scheme here. There is the possibility using seismic attributes to extract more information that are of interest for our interpretation in terms of lithology, petrophysical information, geometrical information, like as I said, the faults, channelized structures, sedimentary structures. And there are different families. I won't speak about the so many classifications that we have for the attributes, but they are, generally speaking, they can be amplitude-based, frequency-based, phase-based, or deep geometrical based on the dip of the reflectors. These are very nice to map again the faults. And so I say, okay, let's look what we can do for our applications. There is a problem that the attributes are very sensitive to the geological variations, but they are always sensitive, in particular some of them, to the noise. And that's why there is a lot of literature in the industry, in journals like Interpretation or Geophysics or so, that are addressing this problem. And there are several tools that have been developed during the time to clean up this data, to remove, to denoise this data. In particular, the random noise is a problem that can create some artifacts that can be misinterpreted as discontinuities, but they are not real geological discontinuities. So processing errors, velocity pull-up also can generate these artifacts. So sensitive to geology, we say the lateral change in geology is sensitive to lateral changes in the noise, and this in particular, some filters that are quite efficient to remove this random noise are the so-called structure-oriented filtering that account for the dip of the reflector and I mean remove the random noise very efficiently without altering, without changing the signals, the good signals. So I focused my research, my first study on the denoising strategies to improve the data quality, also random noise, but for example, there are some tools very efficient. Oh, I'm speaking about post-stack processing. There is nothing dealing with the pre-stack workflow that is, of course, take more efforts and more knowledge possibly. The attributes, I mean, you need to have a geological background, of course, a geophysical background. That is fundamental, but it's sometimes very, I mean, not easy, but you can do it in a reasonable time. You can play with these tools. And so my objective was to clean up the data with these tools, to sharpen the possible faults, to see if there are some possible faults, and to extract fault patterns. There are many tools that can be used. So the first example after these fundamentals, this introduction on the attributes is I provide from the Central Apennine region on commercial profiles we got from the industry. A quick overview on the area. We are, again, Central Italy. Perugia University is somewhere here in the western side. Here is the Apennine Ridge. And there are the area struck by this long and complex seismic sequence start from the area here from Visso down to Amatrice, passing through Norcia, Castelluccio di Norcia basins. It is where several earthquakes greater than 5 were recorded during this sequence, and 9 earthquakes, and the main shock was 6.5 magnitude event. 80-kilometer long area. The faults activating these structures are these northwest, southeast faults, west, southwest dipping, and synthetic and antithetic, so northwest dipping and the southeast dipping. This sequence basically generated in an area that was thought to be active, but that for which we didn't have any record in the Monte Vettore region, in this more external sector, any historical record of strong earthquake, but just geological and paraseismological evidence. And is basically linking to previous seismic sequences. One is possibly you already know because it was very, I mean, also on the television or so. The L'Aquila earthquake in 2009 was very, I mean, we heard many things on the L'Aquila earthquake. And then in the 1997, 1998 was in the northwest side, Colfiorito. So we had a lot of data, seismological, geological, etc. But this is the location, is a 3D view from Google. You see this is the Adriatic Sea, this is the Umbria region, and including the Norcia and Castelluccio basins. And here is the Monte Vettore mountain. And the fault that you see, there is the track of the fault also visible already in Google. That is the the area where the fault produced the ecoseismic ruptures at surface. So there are two intramontane basins that are delimited by boundary faults. Here is a nice peak view on this basin. This is Castelluccio di Norcia, and this is the mountain and the faults that reactivated after about 10 years ago now. Quick view on some peaks. These are the ecoseismic ruptures. I'm 193 tall, so you can see that we got up to 2 meters of vertical throw, plus many others secondary strands, faults, synthetic, antithetic, within the basin that were mapped by the geologist. In terms of geology, we have the Umbria Marche carbonates, the domain, carbonate domain, this important overthrust, and here we have the Laga formation for the siliciclastic deposits of the Laga formation. Here is the geological section that I show you, similar to the one that I showed you at the beginning. You see this bounding faults bounding the basins, this long thrust. And we don't have basically wells in the area, apart this well Varoni that is quite relatively far in the south. So reflection seismic data. The unique data we were able to collect, there were no data in VDEPI, the database. We found only this, we got from any company these two lines, and we recorded the Nord 1 and Nord 2. We got also another in the south, but other basin. So these are the characteristics. You see, these data were collected in the 84 in the period, and they were, you see the trace interval, the CDP interval on the stack is averagely 20 meters, so not very dense, and the general CDP fold for this line is lower than 60 traces. So, and the quality is variable because we had the first line we had was in the paper hard copy. That was this. It was a preliminary processing done in the 84. You see, okay, a lot of problems, migration smiles or so. I mean, the infilling in the basin, it's slightly visible, some reflective targets in some areas, but generally, low quality. Here was the reprocessed version. We had the Seguai in this case, the post-stack Seguai. You see, strongly contaminated by noise. The reflectivity, it's relatively scarce. Some reflectors more visible to depth, but nothing special. For sure, interpreting faults here, it's a complete task. So we decided to work with some starting with simple attributes, amplitude-based, the energy gradient, and this attribute that is my preferred one because it's for structural geologists and for the seismic interpretation is providing an image like this, as a outcrop-like image that is quite helpful to interpret the tectonic structures. And so we tested, this is an extract from the interpretation software, is OpenDetect, I use frequently. This is, you see, a very super noisy line. This is in the Nord 1. This is the line more to the west. And here is the location of the Norcia Basin. Okay, you can see some kind of infilling material, quaternary material, sedimentary material on the top, but it's poorly visible. I mean, the faults is hard to interpret. There are some artifacts like this horizontal line, possibly a filter applied to the data. And so we have also scarce information on the processing that was done on this line. And this strongly reflective target. We tried to clean up a bit of noise. As you see now, I'm scrolling forward and back to show you the effect. I mean, we removed basically random noise, of course, not completely, because then it's always a trade-off, because the risk is that you're going to smooth the discontinuity. So these filters are very efficient, but you should be used with care. And some features start to delineate more, like here. This is the basin, and we said it's bounded by faults. Here is the pseudo-relief attributes that I said is providing outcrop-like images. And it started to show something very, I mean, in the noise, of course, there is still noise. This is the line without cleaning up the noise. Of course, this reflection is quite strongly shown. There is this alignment that is quite interesting because it's exactly in correspondence of the possible antistatic fault. And there are some, again, some features that can be extracted. This is the cleaned, the attributes computed on the cleaned line. That see, it's quite more easy to interpret. There are some reflectivity patterns, some discontinuity that can be followed that I enhanced with this red arrows, the possible two bonding faults. Of course, this reflector is quite nicely enhanced, and generally slightly better improvement with some other features within the basin. Some you see little offset, phase offset between the reflectors. So this is the original, and this is the attribute, the product. And I think the improvement is not that much, but it helps to draw up some possible features. When you have the shallow mapping of this fault, is clearly you can sort of validate this. Here is an image. I'm sorry because the projector doesn't help to, in particular with the green. I see. Here is the envelope. Here was the envelope gradient that here is not very easy to see, but it is helpful to see the dip of these small tiny reflections, particularly the faces that are better visible beneath the basin. And here is the interpretation we provided following the relief. Similar, of course, this image is not very clear, but so what we did is to plot the topography and the track of the fault at the surface, and we derived our interpretation by highlighting a series of discontinuities, steep discontinuities in the west dipping and east dipping and west dipping that delineate a possibly damaged zone. There are many. We just highlighted the main one, but there are different also within the basin. Very nice was the outcome of this low angle reflection, or discontinuity that we highlight with these green dots here, that is interpreted as a regional thrust that was then offset by this fault that is the seismogenic one that at the surface created that 2-meter offset. And so here, this reflector that is we labeled with H is the top regional basement, the top basement, and is particularly visible how here is cut, is laterally interrupted, and there is this feeder dipping this way. So we thought that this fault was going down there, and this is the area basically where the relocation of the earthquake put the hypocentral depth. Here some view in 3D view. Here we used the co-rendered visualization, plotting different attributes at the same time. And this is something also commonly used in the industry. And here we plotted the relief and the energy with the red color in transparency, and you can see some steep features that can be interpreted with faults in both basins. And that we put some, we analyzed the data, all together, showing the difference among the phases, the standard, the conventional line, noisy, and the attributes. And we derived an interpretation also using the DTM, the faults, the faults mapped on the area, the co-seismic raptors that were here the blue ones. And so these are the two basins with the fault that intersect the basin that we derived this interpretation showing that there are even more secondary structures, synthetic and antithetic, within the basins. There are two basins that show similar characteristic. 1 year after, there was a study, was published a study from some colleagues in Rome that they performed within the Castelluccio di Norcia basin a high-resolution seismic reflection profiles, 3 profiles really, more or less crossing the same area. And they also point out that there are some discontinuities in the sediments, in the quaternary sediments, that are very well visible, and they provide their interpretation. And for us, it was a sort of validation of our study, our workflow. So these products can be, of course, reused and can be even improved, in my opinion, working with, again, other attributes. And they were used by other colleagues, published by Collettini in network communication, reinterpreted, also considering the relocated seismicity plotted on the structures. And here is our final model. You see the earthquake, the star is here in the base of this normal fault, the main fault. And here, again, is another interpretation, also considering the geological control, rheological control due to the presence of Triassic evaporites that possibly have a fundamental role in the controlling the seismicity. And here is the star, also highlight that the seismicity is the main shock enucleated in this position. Okay, then the second study, we said I performed in a deeper reflection seismic profile, the CROP-04 in southern Italy. This is the study area in southern Italy. Here is we were involved in a project, a joint project with structural geologists, with some colleagues of different universities. And we got interesting data set from, we collected the seismic lines from VDEPI, the database, we got from the industry. And also we had a chance to have the segue, the post-stack segue of this long line that is the CROP-04. That here is reported in this detail. We extracted the part that was crossing this area, that in the 98 was struck by this 6.9 magnitude earthquake. Is the strongest earthquake in the Ercoli area recorded in Italy. And it is crossing these structures, again, normal faults bounding some basins. Also here the landscape is dominated by the morphological evidence of the presence of these faults. There are basins and alternated with the ridges. With scarps, morphostructural scarps, very well visible. And this was the main fault, the EF, Irpinian fault, that is a northeast dipping fault that generated this strong event. Plus, there are several subparallel structures, synthetic and antithetic. This is the Monticello area with several fault strands mapped by our colleagues, the field geologists. Some overview on the characteristic of this profile. Again, this is the crop was collected in the 80s. Very long profile. As we said, that there are different, the quality of the data is what you see. This is the paper hard copy again, example of the paper hard copy. Some reflections that are somehow strong in some places, but very discontinuous laterally, and random noise present almost everywhere. There are several interpretations of this during the time. Different groups, interpreted this profile in several ways. And you see here is the view of the segue we got, super noisy, and this random noise, dramatic contamination of uncorrelated noise is also reported in some papers by Mazzotti et al., the authors that collect the data and they process the data a couple of times due to some possible reasons. I mean, the poor receiver coupling or many other reasons they list. And they say that possibly with intents, with a new accurate reprocessing, restarting from the gathers, with more accurate statics, with better velocity model, geologically driven, depth migration also can be improved. But this is this is the second reprocessing, and this is what we have. So I said several interpretations. Here I show just an example of an interpretation from Rossetti 2011. He's proposing this model with this long, super long fault, low angle fault, normal fault, and all the faults that he mapped on the surface were linked in his interpretation on this regional structure, analog to a structure we are monitoring in the central Italy, that is the Alto Tiberina structure. And we study several years, we study this fault. So this is a model reproducing this, and we reproposing this in the southern area. And several faults have been mapped, but of course you see now the data quality is what you see. So we said, okay, let's try to, before using the attributes, if these faults, normal faults, as are mapped at the surface, are present, we should see at least in the shallow part something. And I thought to apply the preconditioning workflow to remove the random noise, like in this example taken from the internet, where you see there is no random noise, but after the cleanup, you can see some subvertical faulted structures, some subtle structures. So I applied using this nice software, this OpenDetect, and I have to thank the company DGB Earth Science for providing us the academic license. They are always very kind I'm happy to use this fantastic software. They implemented several of these filters to remove to precondition the data. That is one is the deep steering medium filter that is using basically the dip of the refractor as attribute. It is an attribute itself to let's say drive the filtering, the medium filtering, to remove the random noise. Then we set up an additional filter in the second stage. That was the convolve filter, and then we selected 4 attributes to the same that I shown you before for the commercial line, so the energy and the pseudo relief, and then also the cosine of phase, that is a phase-based attribute, and the similarity, that is a multi-trace attribute, very frequently used in the exploration for the extraction of fault patterns in slice in 3D volumes also. Of course, the attributes are very efficient in 3D volumes, and of course are less efficient in our data, but and this is particularly sensitive to the noise. Therefore, I say, okay, let's try to clean up the data first, and then to apply also, to compute also the similarity and see this. So these are, all of them are independent attributes. So that's why we wanted to test several of them. This is the workflow, the pre-filtering, and post-stack, always post-stack. The attributes, the 4 attributes, we also use the co-rendering, the visualization, I mean, of different of them, and to extract then the fault patterns. This is an extract of the crop. As you see, it's really strongly contaminated by random noise. In this case, there is some kind of reflectivity. You see, in the back, somewhere, and also here in this deeper part, that maybe it's worth to try to let's say improve. So this is after the first pass of the medium filter. You see we remove not all the noise, but a good part. And this is the second filter, the convolve filter. Thus we have from here, we go here, that is I mean, a good compromise. Still, there is some kind of random noise, but we didn't we didn't alter, because the risk is to smooth the discontinuities. And here we found a good compromise. We compute the pseudo relief attribute. And in this case, you can see that it was very effective, with also my surprise, because there are several subvertical, high deep faults in visible, some discontinuities visible down there here, some others that are going in the opposite direction, but also in general the reflectivity pattern is much better visible. There is possible to really follow some structures also here to see some patterns very clearly. Here is the co-rendering with the preconditioned line plot in transparency. And there are some, even some, not only so this that we interpreted then as normal faults very clearly visible, but also some low angle structures, dipping structures like this, that is a regional, we interpreted as a regional thrust that characterize this area, that are again enhanced, that can be picked and interpreted along the line. That seems to have somehow relation with this normal faults. So this is a 3D view where we plot the satellite peak, the original line, and the faults we got from the structural geologist, our colleague Simone Bello and Tal from University of Chieti. We were collaborating with them, and they remapped completely the area with a very accurate mapping of these faults. Here you see, so the red in this case are the S dip, the orange are the west dip, and here is the Irpinia fault, the one that generated this event. So this strong earthquake. Here we see the difference between the original and the attribute output. We can see some strong discontinuities going down there here. Look at this one, and they are exactly in the direction of they are matching very well with the surface evidence. Also here, if you notice, there is the Monte Paratiello structure that is dipping this way, but there are some others. All these are west dipping faults that are possibly the ones that we were looking before in the previous image. This is again a co-rendered image that, of course, help to is outcrop-like image that help to view very well these continuities. This is again another view from, let's say, the bottom side, where we see here is the Irpinian fault again that is crossing down there here the area. There is this system that is quite the Monticello area that are. You see these faults are matching very well with the faults at the surface, and look at the details that we can see in this area. We compute the other attributes, and we use these co-rendering strategies. So here is the relief plus the envelope in red color that also help to enhance the reflectivity, the strong reflections, but also the discontinuities. Here this is what you have seen so far. Here is the cosine of phase that is quite nice to enhance the continuity and discontinuity. And so, for example, here again to pick the thrust, the regional thrust is quite nice. It's very helpful in some areas. And here is the detail on the multiple, I mean, the co-rendered image that where we are plotting the pseudo relief, the seismic line in transparency, the envelope, so the energy, and the similarity that is represented by these black discontinuities here. They are very nicely aligned to the discontinuities, also enhanced by the relief and the other attributes. So they are completely independent attributes that are providing the discontinuities in the same areas. Of course, similarity, as I said, is quite sensitive to the noise. So for sure, particularly in the bottom part, it's possible that, of course, these are not all faults. There is some kind of artifacts, but the red lines that I plot here report all the discontinuities we mapped, also the surface, and that we have a sort of validation of them, and we can extend their position at the surface to depth following this workflow we have done. This is the interpretation we have carried out. This is an extractal detail of, you can draw up many of these discontinuities, these faults. Here is the usual 3D view, including the DTM, the fault from this work, as I mentioned already, from Bello et al., showing the crop and the tectonic structures. And here we published this work a couple of years ago, together also with Ramon, who was on the team, and Ramon Carbonell, and we publish in Frontiers Earth Science this work. So in conclusion, with this talk, I wanted to remark the importance of using this data, even if not ideal, even if they are very noisy, applying some techniques that, this is just a first test, no? There is a lot to do eventually. So preconditioning filters and seismic attributes can really extract more information from the data, and they are very important in seismotectonic studies. We can slightly enhance the signal-to-noise ratio and improve the reflectivity, and particularly enhance these subtle faults that are possibly on the data but are not visible because masked by the noise. We saw that good results, also like in Castelluccio di Norcia, but also on the crop, they can be obtained also for the low-angle structures like the regional truss that are somehow enhanced also. The advantage is that it's relatively quicker and cheaper in terms of efforts if we consider a complete reprocessing starting from the shot gathers. And so it's a very effective tool for the structural geologists, for the interpreters, to extract local details, but also for regional structures. And so this is important in seismotectonics. There is among the disadvantages, of course, they are strongly dependent on the data quality. They are not working. I have some other data where I tried the same and it didn't work, of course. So they are data dependent. There is a part of evaluation and parametrization that can be initially time consuming to test the several parameters for the filtering. And there is the risk, in any case, to generate some artifact that can be misinterpreted. One should be aware of this. And if the filtering is too strong, if you cycle the filtering several times, the risk is that you smooth this discontinuity, that you smooth the reflectors, and you lose the discontinuity that you want to highlight. So the final message is legacy data are unique and not repeatable in this condition, with this configuration. So it's worth to spend some efforts to try to revive, to reevaluating, reinterpret, and improve this vintage data, this legacy data that can provide informations and details on the subsurface, in particular important in seismic areas, in seismically active regions, for supporting geohazard and georisk assessment works. Here I finally report other 3 papers which we use the same techniques. Here there are some data again from the Central Apennine, the same region close to Castelluccio di Norcia, where we clean up a lot of noise and we improve the interpretability. Here is in Val d'Agri area in southern Italy. It was in 2023, I guess. And here is a more recent, it is offshore data, better quality, I mean, pre-stack time migrated data, again, industrial data, where we had very nice structures, salt dye appears that in any case, we clean up the data and we apply these techniques and we really enhance these nice structures. That's it. This is a view of the Castelluccio di Norcia place, a very beautiful place. And so thanks for your attention, and I'm open to questions.
Okay, thank you very much, Mauricio. I think that it's told it was, at least for me, and I think that it's really spectacular, the result that you showed. And I think that it's the measure, it's clear, it is how important the legacy data, especially in seismic, that it's really difficult to acquire new data. So probably it's a good idea just to go back to the old data and try to see that it's possible to extract information that is really valuable.
Yeah.
So probably this is another thing. It's just to the effort that we are, for example, in this institute, just to digitalize all the database and just put it in the public place just for people that is doing this work. That I think that it's really interesting. And the other thing is that is probably the seismic attributes are. I think that it's a really powerful tool.
Yeah. A
new tool that it's providing really spectacular images and improving a lot the images, and this is probably this is a good thing that you can reuse this data that some of them for oil exploration and whatever you can use for example for geosciences or for example for mineral exploration.
Yep.
Because a lot of people is doing reprocessing in this sense, that just to get new images. I have few questions that really short. That it's in the case that it dropped for, you have the experience that you did a lot of reprocessing, pre-stack reprocessing in this data, if I'm not wrong.
No. Always post-stack.
But when you were
here it was the Castelluccio di Norcia.
Okay.
Also, we tried to, because we got the shoot gators, and we tried to reprocess that line that you saw.
So you have
the Nord 2.
Okay.
So yes, okay.
So you have the experience with the pre-stack.
A bit, thanks to your collaboration.
And post-stack processing.
Yeah.
So my question is, it's worth it to do some pre-processing if you have the raw data, or you can just go directly to post-stack data?
I think there is no easy answer. It depends on the context, it depends on the time, on the efforts that you can spend. For sure, if you need something quicker, let's say, maybe you can try this post-stack techniques. I mean, it's worth to try, because they are very effective. They are, as you say, the knowledge on this, it's a lot in the industry. They are poorly used possibly in our context, mineral or in seismotectonics, in the study of the earthquakes. And there is a lot to do, and they are very, very efficient techniques. Of course, on this kind of data, less efficient, but it's worth to try. Of course, if you have time, people, and resources, and the data, because the problem is that sometimes you don't have the raw data, it's worth to invest more energies also in the reprocessing from the beginning, from the shoot gators. But it's challenging. We know I also have, I said, a bit of experience, and we still have to end up that work. But yeah, it depends on the goal and the time and the effort that you want to put.
Okay, so if I'm not wrong, the two examples that you show here, it's from a SegWire file, right?
See, it's from SegWire.
So what about when you only have the TIFF images? So it's scanning the old legacy data and trying to do all this stuff. Do you think that it's effective or not? Or
it's a good question, because we have also the same question. And that's why Elam, my PhD student, is here trying to learn from the data processing, because she's doing a lot of recently for her project, a PhD project. She's working in the Central Adriatic region, in the coast of Marche region, the coast offshore Marche region. And what she has is only PDF data, very low quality, very dark, very problematic. And we said, okay, let's try to digitize, because there are some tools available that also you suggested time ago, you, Ramon, and Juan. And we tried, and so we are learning, and she's learning. She's digitizing several of these profiles, and we are also trying to see if these techniques work on that. But there are some results that are interesting. Again, of course, the quality is even worse, because the digitalization is important, and you can rework, clean up the noise, but there are always some limits. But under certain situations, on certain profiles, we start to see good, interesting results. But she's the expert on this, and so.
Okay. Question.
Lunchtime.
No? Okay. So
Thanks a lot for your time and for inviting me, and have a good lunch.